with stating what the earthquake problem is. Whenever anybody hears that I study earthquakes, there's kind of one question that they ask me. And I think you know what it is, right? What do they ask me? A little audience participation here. What would you ask somebody sitting next to you on the airplane when they tell you that they study earthquakes? Yes. Yes. Some version of that question, of, whoops, it's okay. Some version of can we predict earthquakes? Do you know when earthquakes happen? And when's the big one coming? Some version of that question. And I find it a really interesting question because I think you actually all know the answer to this question. Can we currently predict earthquakes? No. All together now. No. Okay. That is correct here. Whoops. No, I got it. My clicker worked. Right. So the answer is, in fact, no. And you all know it. But the really interesting thing is that you all ask the question anyhow, even though you know the answer. And so does, the other parents at my kid's school, the person next to me on the airplane, and essentially everybody in my life. And so why is that? Right? This is a science talk, not a sociology talk or a psychology talk. But I have a speculation that the answer is that people want the answer to be yes, right? And that it's an important enough question that people keep asking it, hoping I'm going to give them a different answer. So what I'm going to do tonight is kind of walk you through why I keep giving you this answer no, and what hope we have to give a different answer one of these days. And to kind of set the stage here, I should point out that at some level, the answer is kind of yes, in the sense that are earthquakes predictable? If your question is, where do earthquakes occur on this planet? If that was what you meant by earthquakes are predictable, then, in some very general sense, earthquakes occur at the plate boundaries. And there are a lot more of them where I'm from in Santa Cruz, California, than where we are standing right this second. And that's fair, but that's not really what people mean when they ask, are earthquakes predictable? What they really mean is, when's the big one coming? So why can't we predict earthquakes? Or why can't we predict big earthquakes in some way? Well, I better first start by telling you why earthquakes happen at all, and then we can talk about how predictable they are. And to do that, Joaquin, I've just totally mangled your name. The Californian in me wants to make it a Spanish name. Put together this nice little demo for us this evening, which is a couple of heavy objects, some rocks. It's a geology department, they have rocks around, and a bungee cord. And this is a great model of how earthquakes work. Let's imagine the interface between this bottom brick and the table is a fault. It's, maybe the San Andreas right here. And let's imagine that the table is the Pacific plate and I'm the North American plate, okay? And so what's happening is, this will be the North American plate, this brick. Pacific, North America, San Andreas. And I am the mantle of the earth. That's what I'll be today, which is always moving. That's the layer underneath the plates, always moving and tugging and tugging and tugging and tugging and tugging on the plates. And eventually, when it tugs enough, the fault slips forward. That was it. That was your earthquake. So let's just think a little bit about what happened here. The mantle's moving. This bungee cord got stretched out. That's the elastic stretching of the crust, storing up stress, strain energy. And then when that stress, this bungee cord gets tight enough, overcomes what's holding the fault closed. That's friction, the friction between the brick and the table. When it overcomes the friction, oh, I'm having a hard time making an earthquake. There we go. Then it makes an earthquake. Right? So that's it. That's the basic physics of the process. And so at some level, this should be a very, very predictable system. We have stress accumulating in the crust. That's me stretching the bungee cord stressing, 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 and eventually hit some threshold in strength. That's the friction. And when the stress hits the strength, then the brick slides forward, the fault slips, releases the stress, so the bungee cord got loose, and then we repeat the cycle as the mantle continues to move. So far, so good? And so if this is all there is to it, predicting earthquakes should be easy, right? You figure out how fast the mantle moves, how fast the plate moves, how fast stress is accumulating. You figure out what the strength of faults are. The strength of faults are the frictional coefficient is typically of rocks in the lab around 0.6. It's something we call in geology Byerle's law. As you will learn during this talk, laws are more like guidelines, but geologists are not very law-abiding. Certainly the rocks aren't. So a coefficient of friction is what determines the strength of a material. So just remember the number 0.6. And then when you get to that strength, you release and have an earthquake. So easy peasy. Let's predict earthquakes. What's the problem? The problem is this is possibly a more accurate view of the system. That the strength is highly variable over time. Maybe not this variable, but it can be. Water moves in and out of a fault zones heal. There's chemistry involved. It's terrible. I hate chemistry. I'm a physicist. Not my thing. But then if you're going to study fault zones, you got to deal with chemistry. And there is stress accumulates at variable rates because the mantle's not perfectly steady because there are nearby earthquakes. The system's always changing a little bit. And the strength, the stress released in each earthquake might be different. This is called the stress drop. And so by the time you're done with this, you're like, what in the world is there to do? This is an impossible problem. I'm going to move on and study glaciers. They're much easier. So what we need to do is somehow reduce this to a slightly more tractable problem. And so let me focus for a minute on a subset of these problems, which is what is the stress at the end of an earthquake? So where does this line bottom out? And that's an interesting thing to focus on because it sort of sets the stage for the next cycle. If you're accumulating stress or equivalently energy in the system, if you're bottoming out, your final stress after each earthquake is at some relatively high level from zero, then it's at least theoretically possible to have another earthquake to hit some strength kind of at any time. You don't have to, because there's this, the bungee cord is preloaded, it's pre-stressed. And so having another earthquake, I'm about to leave the end of the table here, but is really easy when it's preloaded. But if, on the other hand, the stress bottoms out to 0 at the end of an earthquake, then there's at least some degree of predictability in the system. That's what we want, right? We want to predict earthquakes. And that some degree of predictability, you have to re-stress the bungee cord before you can have another big earthquake, at least. There's no energy left. So maybe we could just answer that more restricted question first, to ask ourselves, is there some degree of predictability in the earthquake system? You game? All right. So I want to know what the stress is at the end of an earthquake. I got to better reset this set of blocks. Well, the stress required to make the earthquake is overcoming some static friction, the friction at velocity 0. And the stress at the end of an earthquake is determined, there goes that's it. No more earthquakes. I broke the loop. Fun. The stress at the end of the earthquake is determined by the dynamic friction, that is the friction while it's sliding. Because while it's sliding, there's some resistance, and when you finish sliding, that was the final force on the block. So what we really need to know is both the static and the dynamic friction, in particular the dynamic friction, to know the stresses at the end, to know whether or not it's predictable. You guys with me? You're allowed to say, no, I have no idea what's going on. I don't mind. It's a small audience. It's cool to interrupt. We're good? Okay. Now, measuring the dynamic friction is pretty complicated because that means measuring the friction on a fault while it's moving. We can do that in a lab. As it turns out, when we do it in a lab at high speeds, we actually get quite a lot of different coefficients of friction. It's not anywhere near as constant as that 0.6 I said for static friction. But what we really want is in the real Earth to measure the friction on a real fault while it's moving. All right, now I just said we don't predict earthquakes. So this is going to be quite challenging. We need to get some instruments onto a fault, and we don't know when the fault's going to move or which fault we want to instrument, and then we want to get some friction meters down there. So that's a problem. There is a way to get at frictions, dynamic friction, after an earthquake's happened. And that is by taking a fault's temperature. How do you do that? Well, okay, everybody with me? Why don't you rub your hands together? Okay, what happens? It gets warm. We're making heat energy here, right? Stop rubbing. Are your hands still warm? The earthquake's over, sliding past each other. That's the earthquake. Earthquakes are rocks sliding past each other. They're not this, they're not squishing, they're sliding. And so they're sliding, and we're all done, and our hands are still warm, even after the earthquake is over. So if we get there fast enough before our hands cool off, and stick a thermometer in there, and if we knew how many times we rubbed them back and forth, the distance, the thermometer will measure the heat energy. Going back and forth, that's the displacement, and we can work out a force off of that, and we can work out the frictional force. So that's the strategy. Let's stick to an earthquake that slipped really a lot, so it should have released really a lot of heat energy, and get there as soon as we can after the earthquake and stick a thermometer in it. So that's going to involve drilling a hole and sticking it in, and then come back and take its temperature and see if we can work out the friction. Not an easy enterprise, and you need to start out with a really, really big earthquake. And so this strategy had been tried on a number of earthquakes starting in the late 90s. And a bunch of us had gotten together and thought about what it would take to do it right. There were definitely some lessons learned. And we kind of worked out a plan, and then we waited for an earthquake. And the earthquake that turned out to happen was the 2011 magnitude 9 Tohoku earthquake, which is the largest instrumentally recorded slip ever on a fault. This contour done immediately after the earthquake suggests there were about 50 meters of slip on the fault. Actually, it was probably closer to 70 meters from repeat bathymetry out by the seafloor. So here we go. Let's go take its temperature. Well, where it slipped the most is out by the trench. It's where one plate comes under another is where it slipped the most. And where one plate comes under another, the top plate bends down, and those are among the deepest places in the ocean. So there's 7 kilometers of water on top of that fault. At the time this was done, in 2012, nobody had ever drilled a substantive hole of any kind under 7 kilometers of water. It's actually quite hard, because all the motor control on the drill ship all your steering is from the ship itself. So you're like dropping a pipe to the bottom of the ocean and then kind of steering it by moving the ship. All right, you see, that might be a problem. And there's actually only one ship in the world that can do it, which is the Shikyu, owned by Japan. And fortunately, Japan felt very obligated to learn as much as possible from this catastrophic earthquake because it was so societally damaging. And so, the JFAS expedition happened, and we were successful. Among other things, we picked up a piece of fault. Here it is. This is the plate boundary fault from 800 meters below sea floor. This black scaly fabric. Matakari took it into the lab and measured its low speed, that is static coefficient of friction, what you have to overcome to get it going. It turns out it's not 0.6. It's 0.24. It has a lot of clay in it. Okay? So that's 0.1. No Byerly's law here, 0.24. And then we went ahead to measure the temperature. So, this is obviously high budget science, but even big projects at some point come down to duct tape. This is 55 temperature sensors duct taped to a piece of climbing rope and dropped into the hole and then pulled back out 9 months later. And this was an extremely exciting moment. I was actually not on the ship at this time, but the team sent me a picture. And all 55 sensors came back and in this undeformed hole, which we weren't totally sure was going to happen because all the data was on flash drives on the temperature sensors. So like if the rope didn't come back, that was it. There was no data. But the data came back, so that was awesome. And so what's it say? So this is sort of a zoom in on one section of the data where you see there is from 800 to 820 meters depth. Each of these lines is more or less a sensor. And the x-axis here is a function of time. So deployed in July and August, and then in December, there was actually a big aftershock. So I'm not showing you the data after that because it's kind of a different story. I'm just cutting it off before the aftershock. And the colors are the temperature of the data relative to the geotherm. In general, the Earth gets warmer as you get deeper. So we're going to take that effect out and look at anomalies relative to that. Okay, so I've left this up here long enough that you can stare at it and see. Well, there's a couple of things you should notice. First of all, it started cold and then got warm, which is a little confusing after an earthquake. You thought it would, your hands started warm and then they cooled off. That's because when you drill a hole at the bottom of the cold ocean, the first thing that happens is it fills up with cold seawater and then has to re-equilibrate. And so that effect has to be sort of taken care of and taken out of the data. In addition to that, I think you might notice this big red thing down here. That's the fault. That's, according to the lithology, that's where the fault is. And it's warm. We got a 1/3 of a degree temperature anomaly. Yes, 0.3 degrees. That was the goal. And so we could actually compare that to a model of if we put frictional heat onto the fault. The right-hand side is a diffusive model. And we also model the warming up of the seawater in that hole. What we need to do on dissipating frictional energy on the fault is get a coefficient of friction that's around 0.08 is our best fit value, and with a 90% confidence interval between 0.05 and 0.19. Anybody remember Byerly's law? Which was 0.6, and it's lower even than the static coefficient of friction, which was 0.02. I'm sorry, 0.24. So what we conclude from this is that the high-speed friction is much less than the low-speed friction, which is less than Byerly's law. On this fault, in this one hole at 800 meters fault depth below seafloor. Okay, cool. So at least it is plausible here, with this very low friction, we have essentially a complete stress drop, or very nearly so. That's actually supported in this case by the earthquakes right after the Tohoku earthquake. Some of the aftershocks went in the opposite direction as the thrust earthquake. And so that suggests that the compressional stress was completely relieved. So what do we get out of all this? A lot of cool pictures, and the conclusions from the JFAST drilling project is that a complete stress drop is possible, at least in one spot for one earthquake. So the implication is there's at least some degree of predictability of this in the system, that at least earthquake cycles might exist or can exist. Great. So I'm going to call this approach number one, as in method number one to study earthquake prediction. What you just watched me do is sort of approach the problem like a physicist. That I sort of reduced the earthquake problem to a series of forces. I even made a little model, or I didn't make, but used a little model of a bungee cord and rocks, and worked out how to balance the forces and what I could actually measure in the earth, and deal with that as a physicist. That's not the only way to study earthquakes. In particular, you might notice that this measurement was in one spot, right, in one hole. I mean, it was a big hole, but it's one hole on the seafloor. And faults are not homogeneous, simple things. They have a lot of structure to them. And in particular, we think faults have both strong bits and weak bits. We often use the word asperity, which is kind of a technical word in friction, but it means bump or strong spot. And the idea is that faults might be nailed closed in a few areas with very strong friction, and very weak pervasively, perhaps, maybe, I don't know, but it's a possibility over much of it. And so a single measurement of friction tells you something. It's certainly useful to know that a complete stress is possible and that Byerly's law is not the only thing in the story. But it's certainly not telling you everything. Rupture may begin in strong spots when you break a nail and then slip, with the total stress drop governed by the spacing of these nails of these strong spots. So what do you do with that? That was a very expensive hole. We're not drilling any more of them, or certainly not a lot of them. Actually, a few of them, more of them just got drilled this fall as a repeat visit to that site to make sure that we weren't wrong the first time. They terrified me, those holes. But still, we need a little bit of a different strategy here. And so I'm going to move to approach number 2, which is to look at faults themselves and ask what information does a fault contain about the variability of strength in the earth. And faults are really interesting objects. They have a lot of structure to them. This is an exposed fault in a quarry in Oregon. And studying faults directly, the rock record directly, maybe I'll call this approaching an earthquake as a geologist rather than a physicist. And so one thing you can measure about this exposed fault surface, so just to get you oriented, this is one side of a fault that slipped this way, a normal fault, and one side of the fault's missing. So it's like you're just looking at the table and not the brick. Okay. And so what you can do is measure the topography of this fault, the bumps, how, where it goes up, where it goes down. That's a measurable, observable quantity. I started out doing this quite some time ago with this now very old-fashioned looking ground-based LiDAR, and taking the measurements of the roughness of faults. And I admit I got a little obsessed. And have spent much of the last 15 years, I'm not entirely sure why, measuring the roughness of faults. And we have learned a lot of things through that. When we compare different faults, what we can see is some faults are relatively rough, particularly faults that have not slipped a lot, like this little surface fault on Mount St. Helens, right on the edge of an eruptive plug. Some faults are smoother, and particularly mature faults get a lot smoother. And this is true at a variety of scales. We've measured ground-based LiDAR, we've done drone measurements, we also have taken hand samples into the lab and used white light interferometry, and at all scales, you can see some differences and some systematics in how roughness behaves. So immature faults are rougher than mature faults. That's the take home there. We can also see the same property on traces of faults. That is, if you look in map view at a fault, say a strike slip fault, and just watch how it wobbles around on the earth, immature faults tend to be very broken up with lots of splay faults and secondary faults, and mature faults smooth out. When we compare the systematics of fault roughness to various properties of earthquakes, we find there are some patterns. This is recent work that Weiyun Guo, who just graduated from our group, did. And what she found is that very immature faults tended to have lots of aftershocks and move a little bit slowly. That the rupture velocity, the speed at which the fault starts slipping is slower on immature, these rough systems, than the mature systems. So that's suggesting a different kind of earthquake predictability, that if we approach the problem as a geologist, maybe we can't predict when the earthquake's happening, at least not from this data, but we can predict what kind of earthquake. One that, zips along really quickly or moves a little bit slowly as it bumps its way along all these secondary faults. We could also predict so whether or not it's going to have a lot of aftershocks. These very immature systems have all those secondary faults that get activated. So the aftershocks, you have an earthquake, and it hits another fault, and it hits all these secondary little splays and makes lots of aftershocks. And the very mature systems, actually, somewhat surprisingly, don't have a lot of aftershocks, we think likely because they're not hitting the whole secondary system. There isn't as much of a secondary system to hit. And so now we have a different kind of predictability. Fault maturity predicts the kind of earthquakes and the overall kind of sequence we're going to get. All right, that's useful. Still not quite the question you were all asking in the beginning, when's the big one? But it's still a useful type of prediction. It also suggests another way to think about the earthquake problem, which is rather than trying to predict individual earthquakes and individual, say, aftershocks, we're starting to see some systematics kind of statistically. We're thinking about the fault systems here, and we could predict that maybe some of these guys are going to have earthquakes on them after this one ruptures. So there's a different approach here in thinking about the fault system. So let me run with that. It's speeding up now. Approach number 3. Approach number 3 to the earthquake problem is to think about these faults as a network, as a system of earthquakes triggering earthquakes, triggering earthquakes, and what the statistics of that problem are. Maybe I'm now thinking about the earthquake problem as a statistician or even perhaps a mathematician or computer scientist. We're actually pretty good about earthquake prediction in this sense, that when you have a big earthquake, it almost certainly has aftershocks. Almost all earthquakes have aftershocks, and so we can predict that. We can do more than just predict that you will have aftershocks. We can predict how many aftershocks you're going to have. And there's this lovely thing called the epidemic type aftershock sequence model, ETAS to its friends, which is a statistical model that's been out there for 30, 40 years now in earthquake world, which says if you have one earthquake, it's likely to have a certain number of aftershocks based on the magnitude of the original earthquake. Bigger earthquakes have more aftershocks than little earthquakes. Each of those earthquakes are going to get spread out in time. More of the aftershocks will happen right after the main shock, and there'll be fewer and fewer and fewer as you go out in time. This is something called Omari's law. And each of those earthquakes have some probability of becoming big. So you're starting to think about this as an epidemic, one earthquake making another, or maybe a family tree if you want a less gory analogy. And in general, on this planet, there are 10 times as many magnitude 4s as magnitude 3 earthquakes, and 10 times as many magnitude 3s. Wait, I said that backwards. Let me try it again. There are 10 times as many magnitude 3s as magnitude 4s. There are more little ones than big ones. 10 times as many magnitude 4s as magnitude 5s, 10 times as magnitude 5s as magnitude 6s, factor of 10 for each magnitude. So each of these children earthquakes has some probability, if you draw it random from that distribution, of growing up and becoming big. So you stitch those things together, a magnitude distribution, a time distribution, and a number of aftershocks as a function of magnitude or main shock, and you have a statistical model. And now we can think about earthquake rates statistically as a predictable phenomenon based on the prior history. ETAS is, as I said, old. These days, my group and various other groups have moved into the machine learning era and tried to rebuild this sort of statistical model based on prior history of earthquakes, predicting future earthquakes. Our particular approach is something called recast, and we beat the performance of ETAS by this much. And we're very we're very proud for ourselves for doing so. Likely the machine learning method was learning about a lot of inconsistencies in our observations of earthquakes, inconsistencies in the catalyst. Sometimes you're able to observe the little ones, sometimes you're not. And so that's likely why we're beating ETAS. ETAS is actually a pretty amazingly good model for how earthquake occurrence works. It gets it right, 99% of the time. What it tends to miss is, of course, the ones that everybody cares about, which are the big ones. It does a great job of predicting all those little aftershocks. All right, well, so that's a statistical approach. Even though it's not getting the big ones, let's just run with it for a minute. And let's see if we can try to understand why this statistical approach is working as well as it's working. And one way to think about it is to try to look at how earthquakes interact with each other. How does one earthquake trigger another earthquake? After all, they're all making aftershocks, right? How's that happen? And there's a number of different processes by which that happens. One of them is through dynamic triggering. That is, when the seismic waves from one earthquake, say this earthquake, oops, I am struggling with this pointer. If one of these, when the seismic waves from one earthquake, this is an earthquake in Alaska, hit some regions that are particularly sensitive. This case is near Yellowstone. These seismic waves are able to trigger local earthquakes. Notice this is really far away, 3,000 kilometers away. And what you're looking at on the middle panel is actually exactly the same seismogram as the top panel. The y-axis changed. It's exactly the same seismogram gone through a high-pass filter that removes those long period waves that are able to easily travel from Alaska to Yellowstone. And what you're left with is all those very, very high frequency waves that actually aren't able to travel far in the earth. They get attenuated and absorbed by the earth. And so they're showing you all these little local earthquakes popping off in Yellowstone. And it's cool because these earthquakes are being made by that wave. There's like no question of what's making those earthquakes. They weren't here before the wave got here, the wave got here, they're making those, I mean, you don't have to do fancy statistics to see that. We will do fancy statistics in a minute, but this is really obvious. And that's a pretty neat natural experiment because we observe this wave makes this earthquake, so we know what stress is arriving, how hard you're hitting the earth from that incoming wave, and we know what the effect of that is in terms of earthquake rate. If we can calibrate that more generally, we would learn something more generally about this earthquake system and how earthquake rates are triggered. So let's do that. So what I'm now showing you is earthquake rates. The change in rate divided by the background rate. So 1 here is a doubling of the earthquake rate, where the change is just as big as the original rate. As a function of the velocity, how hard the ground shook on the incoming wave. Stacked together, combined for all of Southern California from '84 to 2008. And the red ones are from far away earthquakes. The blue ones are a little bit of a cheat, but they're from local earthquakes. As you can see, you hit the ground harder, you make more earthquakes. Cool. Not totally surprising, maybe, but cool nonetheless that that's observable. So what does that mean? How do we interpret that? Well, the peak ground motion in terms of how fast the ground's moving up and down is proportional to the strain in the elastic waves. Strain is how we measure how much something stretches. like how much did the bungee cord stretch, or in this case, how much does the ground stretch from the seismic waves. And so, and how much it stretches, how much the ground stresses is proportional to the stress, the force, pulling on the fault. So we can interpret this data in terms of a distribution of stress that needs to be added to the system in order to make it fail. Coming back to our original figure of stress accumulating relative to strength, what this observation is telling us is that if you hit the ground with just a little bit of ground motion, you'll sometimes, very rarely, get a handful of faults that are really, really close to that strength line. Some faults will be so close to that failure line that they're going to get pushed over even by a teeny tiny millimeter per second wave. Whereas if you hit the ground with a much larger wave, then you make the fault that was really close to failure fail, make this guy fail, or these guys fail, the faults that are sitting right here on the stress curve, but you also make the ones that were sitting very far away from the failure curve fail as well. You make all of those earthquakes happen. So that's many more earthquakes. So what that tells you is that this measurement of amount of triggering as a function of peak ground velocity is actually a way to measure in situ distribution of stress in the crust. And so that the number of faults that are within some epsilon, some strain of failure, is being measured by how much the earthquake rate changes from the stress, from the incoming wave of a particular amplitude. That was a bit of a mouthful, but you guys with me? All right. So, approaching the fault system as a system has been perhaps a little bit more illuminating on our earthquake problem. But as I said, we're predicting little earthquakes here. I mean, yay, we get a doubling of the earthquake rates, but if they're still all magnitude 2s and 3s, as the vast majority of them are, that's not really what most people mean by earthquake prediction. So let me keep moving and find another approach on the problem. Approach number 4, and this will be the final approach, is earthquakes in a geological system. Wouldn't it be cool if there was something different on the fault, something, say, observable on the fault prior to big earthquakes? I mean, that's really what everybody wants. They want to see maybe the fault slipping slowly as I stretch out the bungee cord before it slips quickly in the earthquake. That would, and if it was different, it slipped in a different way before big earthquakes. That would be really cool, right? That would be like a genuine precursor. And so to look for those, we need to go look at specific faults in nature. And this is, I think, the first map I've showed you the whole talk, right? Maybe, all right, fine, there was a little location map in Japan, but there wasn't much. In order to start looking for those precursors, we need to actually put the faults in space on the Earth and think about them in a geological system, and maybe we're going to call this geophysics. One of the, in my opinion, most exciting advances in geophysics in the last 20 or 30 years has been the discovery of slow slip earthquakes. And these are earthquakes that move in slow motion, and they're found particularly in subduction zones, primarily where one plate comes underneath another. And one of the case examples in this particularly pretty picture comes from the Seattle region, Puget Sound region, where this map is showing you the total slip on the fault going down one plate, the fault's on this downgoing plate underneath North America, And this map of slip looks a lot like that map of slip I showed you for the Tohoku earthquake, but this is happening in slow motion, that each panel here is like 1 day of data over a full day rather than a few seconds or tens of seconds. So that's a slow slip earthquake. Now, wouldn't it be cool if these happened before big earthquakes? Well, there's a teeny bit of evidence they do. Teeny bit. And it comes from 2 earthquakes, one of which is the 2014 Iquique earthquake in northern Chile, where there was slow slip over the weeks leading up to this magnitude 8.2 earthquake. Now, it took a while to really, it's hard to know exactly what that slow slip will look like because all the instruments detecting it, all the GNSS were onshore and the earthquake and the slip was offshore, so that's not great. We need the instruments offshore where the slip is. But nonetheless, it's pretty compelling that there was slow motion before this earthquake. Now, one earthquake with some slow slip before a precursor does not make, right? That's just an interesting observation, not an earthquake prediction. What we need is some system that has lots of slow slip before an earthquake. And that brings us to Antarctica. Huh? Bear with me. Let's go to the Willands ice stream. The Willands ice stream is in Antarctica. And it has slow slip events and earthquake-like events on its base under 800 meters of ice where it hits the bottom frozen rock every day. They're actually tidally modulated as the ocean pulls the tongue up and down. You get these massive slip events, like 100-kilometer long slip events, so like magnitude 7 earthquakes every day. Well, that's cool. You can put instruments out there and study them every day. And because it's just the base of an ice stream under 800 meters of ice, they're actually a lot closer to your instruments than typically we can get on faults, where we'll often have kilometers of rock in the way. So what do they look like? Well, they're pretty neat. There are sort of 2 flavors of these slip events. Some of them start emitting seismic waves at a place up ice called Ice Rise A. I've never been there, but I'm told if you spend enough time on the ice, it starts to look like a hill. Some of them begin downstream on the grounding line, right where the ice is floating out over the ocean. And in both cases, the place that I'm marking as them starting with the star is what I mean by starting is the rapid slip starts there and they emit seismic waves. When some GPS instruments went out there, or GNSS, what was found is that the ones that rapidly start slipping where the blue star is actually have a precursor. They start slipping slowly where the orange star is, but before they slip rapidly. Oof, I have trouble saying that, but look at the figure. And so there's this slow precursor starting like 60 kilometers away. This is a big region. And then that slow slip migrates in to where the rapid slip happens, and then it goes bang. It breaks the little asperity, breaks that nail, and then it zooms back, zooms off, and emits seismic waves. And the opposite happens in the other direction. You do have events that slip quickly on the grounding zone, but they're preceded by slipping slowly up ice. So that's cool. And that's a little bit like what we were seeing in Iquique, where something slipped slowly and it swept in to the place where ultimately there was an earthquake, and then the whole thing released. So what do we think?
The X scale.
The X scale, oh, you're right, I got rid of the X scale here. It's about, tick marks are about 10 minutes. Whoops, sorry about that. So we have these precursors in both cases. So what we think is happening here is that there are places on this ice stream, I want to call it a fault. It is a fault. It's just the fault where one side's ice, where it gets stuck and builds up a lot of stress as it's seesawing on with the tongue floating on the ocean. But my caption's over keywords here, but that's not where slip begins. Slip begins where the frictional stress is weakest, where it's pushed down the least, where there's a very weak spot that's not stuck. And that's where slip begins. And then it migrates in till it's pushes over this high normal stress region, these strong spots, the nails. And then when the nails break, that breaks rapidly, emits a lot of energy, and that's the seismic waves. All right, I'm almost out of time here, so let me kind of try to pull it all together for you. I've told you a lot in the last hour. We started out with the question, the earthquake problem. Can we predict earthquakes in some form? And we all say no, we can't do it. And I still agree, no, we can't currently do it. But we are still obligated, at least I'm obligated, not you, but me, as somebody who studies earthquakes for a living, I'm using quite a lot of taxpayers' money to study earthquakes. I am obligated to grapple with this problem. That's my job. And I think we can meaningfully grapple with this problem. We can grapple with it in 4 different ways, at least, that I discussed here. One is looking at earthquakes kind of one at a time in isolation. That's what I kind of tongue-in-cheek called the physicist approach. And when we did that, we learned something. We learned that co-seismic friction is much lower than static friction, and complete stresses are possible, which in fact implies there's some predictability in the system, which is not a totally hopeless case. Hey, I'll take it. Then approach number 2 was earthquakes on faults, what I call the geologist approach. And we learned from that mature faults are smoother than immature faults. I will say, for those of you who are coming back for tomorrow's talk, I'm going to talk more about what we can learn about from roughness of faults, but for here, this is what we said. And that fault maturity controls rupture velocity and aftershock abundance. And so geology predicts the kind of earthquake that we get. Approach 3, earthquakes on fault systems, the statistical approach. Triggered earthquakes are predictable by dynamic strain. This is starting to look like real prediction. At least earthquake rates are predictable. And in fact, can even be used as an in situ probe of fault cycles. Where you have faults, how many faults are just a hairbreadth from failure, how many faults need to be pushed really hard in order to make an earthquake. Again, coming back to that tomorrow. And finally, earthquakes in geological systems, I like to call this the geophysicist approach. In some areas and some time, faults slip slowly, and slow slip can precede, maybe even predict, fast slip starting 50 kilometers from a hypocenter of an ice stream event. And the fact that at least there exists this model system out there in the ice stream suggests that, for real, sorry Ian, for real faults that are made out of rock, that we have some physical reason to expect that we might be able to see slow slip precursors, and it may be occasionally we have. So what do we do with all that? I think if you're going to sort of try to extract some philosophy from this, um, one of the take homes I would like you to take home is the power and context of context and a natural experiment. The most satisfactory answer to the can we predict earthquakes question, I think these answers get incrementally more satisfactory as we went through the talk. And the most satisfactory ones are when we knew a lot, when we knew where the ice stream was, when we had a forcing either from seismic waves, which was we know the input, we know the output, or the tidal strains, we know the input, we know the output. Those are really useful experiments. And that's how we're going to make progress on the problem, getting a lot of data in context with a natural experiment. And so something I'm spending an inordinate amount of my time these days doing is leading an initiative called SZ4D, which is subduction zones in 4 dimensions, the 4th dimension being time, which is an effort to put a lot of brain power as well as a lot of instrumental power together in the places where we have the best natural experiments. And the best natural experiments for earthquakes, as well as for volcanoes, and I will argue as well as for landslides, are where plates converge, where there's a lot known about the system, and so we can ask what stress causes what event. And so we're working to build out our instrumentation in the world's most active accessible margin, which is Chile. Also a place where we've actually seen at least hints of precursors. And we're also trying to build that knowledge in a way that we can bring it home to our domestic subduction zones, most notably Alaska and the Pacific Northwest, Cascadia. So that's the next big thing. And I will stop there. Thank you for sharing your evening with me. And are there any questions? Anybody still awake? Okay. You're not a student, but that's, I'm just going to let you break the ice here. Okay, go for it. Yeah. I think it's a real, I mean, so I believe it's a real thing. It is really the temperature diffusive front. That's the error function coming down. There is an instrument spacing thing that makes it look sharper, okay, because it's only one row. So it looks like it's one row per instrument. And so the instrument that showed it to the instrument that didn't is the diffusive front. I do think it's real. It is sharper than I would have liked, but it makes sense in terms of the thermal diffusivity of rock as measured. Most of the error bar is from errors on measuring the thermal diffusivity of rock in that problem and the timing of when this was taken. All of that said, there's a new installation that just went in October. To try to remeasure that anomaly 10 years later, and it better have moved. And if it hasn't moved, I mean, this is terrible. This is like how you prove yourself wrong, but that's good. That's how we're supposed to do science. And so when that data comes back, we'll know whether or not that front moved, which it should have in the intervening 10 times, 10 years. Other questions? Yeah.
Also consider like timing as a predictive quantity and when it occurs.
Yes, so it's all embedded in earthquake rates. So earthquake rates are actually surprisingly predictable. What's harder to predict is earthquake size. So I can tell you there'll be at least 5 observable earthquakes in California tomorrow. And most likely they will be drawn from this magnitude distribution I was telling you about, known as the Gutenberg-Richter distribution. There'll be many more little ones than big ones. So there is a statistical chance, 1 in a million, that one of them will be a magnitude 6 or 7 or bigger. But it's hard to do better than that. That's the benchmark of ETAS, the epidemic type aftershock sequence model, and that's the benchmark that it's been shockingly hard to beat. Everyone tired?
Yeah, probably.
Yeah, sure.
Do you measure capacity of the rock to accumulate stress?
Keep going with that question for a minute. Let me think of what you need.
Because probably the large earthquakes are because of large release stress. So probably measuring the capacity of some rock
I think I'm following you.
would say something about.
Yeah, so how much I'm able to stretch this bungee cord, how much strain I can put into it, determines how big an earthquake this thing has, right? That's basically what you're saying. And that's true. The springiness of rocks, for the most part, is pretty similar. So the stretchiness of most bungee cords and most rocks is pretty similar. What varies a lot in the earth is the history, and there's sort of a patchwork quilt of places that are still stressed and accumulating stress and places that release stress recently. And so that adds up to an energy budget. And so to actually ask whether or not you have could do a big earthquake, the energy has to be there. And so it's not so much the capacity of a rock to accumulate stress as how much energy is over the whole system that determines whether or not you have a big earthquake. Did that answer make sense? Yeah, okay. Yep. I was trying to think about that as it happened as well. Sure. I'm going to stretch it here because I'm thinking on the fly, but how about a magmatic intrusion or even a hydrofrac? Anytime that you shove fluid into the crust, that opens stuff up. That is faults are fractures that slide. If I slide my hand in between here with some magma coming up from the deep crust, or if I push some water down a well and use that water to sort of pry apart the bungee cord and the fault, that's a opening fracture, and that sort of shadows and insulates this piece of rock from my further stressing. It is meant to represent the elastic crust. So the actual geometry here is, say my hands on the fault, on the San Andreas. This is the Pacific, this is North America, okay? And it's sliding like this. North America's moving relative to the Pacific, and so my forearms are more or less the bungee cord, because they're getting stretched by my elbows moving, while the fault remains locked by friction most of the time, and then eventually when my forearms are stretched enough, it jerks forward. Does that help? Yep.
So you brought up Chile earlier and how like that is like a main place to like study and stuff like that. Has there been any like discoveries y'all made of recent or any like upcoming projects that y'all plan to do in Chile that are trying to, I guess, answer the earthquake problem that people have?
Oh, yes. So there is a fair amount of instrumentation that has been built out there ever since the 2010 Maule earthquake, which was another magnitude 8 and change earthquake in Chile. There's a pretty advanced seismic network there, but there's almost nothing offshore. And as you can see, you really need to get close to, wasn't it wonderful on the ice sheet stream when we could get close to the fault? It's a totally different experience. So what we really want is seafloor geodesy. We want to measure the slow motion of the earth close to the fault, as well as maybe some seismometers out there. And also to, I didn't really talk about it today, to measure the other hazards and how they interact, because those all give you your natural experiments. When the earthquakes hit the volcanoes or the volcanoes hit the earthquakes, those are all known forcings that make the other system react. So we have under consideration at NSF a center proposal, which means a sort of large-scale collaboration where we all think together about the system. Hoping to hear any day on that. It's been at NSF for a year, so I think now's a good time for a decision. In addition to that, we are proposing through something that is called the Mid-Scale Research Initiative, MSRI, at NSF, to put out the instrumentation I just discussed, to do the seafloor problem and to do it right, as well as to instrument all the way from the trench to the volcanic crests, so you could get all the interactions. That is a proposal that will go into NSF as soon as they release the call, but they haven't released the call yet, and everything, in case you didn't notice, is a little delayed in DC at the moment, but we're anticipating that shortly. So that's where we are. Yep.
When we're talking about the explosive earthquakes, is it the same thing as like creeping faults, like those almost interchangeably, or what would the difference be?
So a creeping fault classically is one that is always moving slowly. So the central section of the San Andreas is not locked. It's always keeping up with the plate motion. And a slow slip event is creep that happens episodically over maybe hours or days or weeks. How are we doing? Can I keep them here forever? Or should we let them go?
We should let you go
Yeah, I imagine you're ready for a break, but
after 12 hours.
I mean, if there's any more questions?
I'm happy if you guys feeling a little shy in front of each other, you can come on up and ask questions.
I mean, just a reminder, Dr. Brodsky will be at Hitchcock Hall 31 at 1:45 tomorrow for the technical lecture, so there is another opportunity to pick her brain some more. But otherwise, thank you very much for an excellent talk.
Thanks for the opportunity.
Thank you everyone for coming.